Today, first of two lectures where we cover HVAC. So today I'm going to do the introduction, and Wednesday Stet's going to show us some more advanced integrated systems. So in the introduction, I want to give you a brief history of air conditioning and go over some of the fundamentals to get you familiar with the language of HVAC types of systems.
I never thought I would do it again.
Somebody probably wants to mute. All right, so you've seen this triangle before, right? I've shown this several times. And in terms of our teaching sequence, Architecture 140 starts at the top and moves down. But important point I want to make here that is in practice, the design of high performance buildings is not a linear progression through this pyramid. The best buildings are created by interdisciplinary collaboration early in the design process, and you're often iterating through these different steps. So what does HVAC mean? It stands for heating, ventilation, and air conditioning. Sometimes you hear the industry refer to HVAC and R stands for refrigeration. So if you're in a building that requires food storage or other kinds of refrigeration, sometimes you'll hear HVAC and R. So I want to start with a brief history of air conditioning. I kind of enjoy that. Some of you might as well. This silly photograph was an advertisement in the 1950s, and I'm going to come back to a little bit later in the lecture. So let's just start with heating. So shelters always sought to modify the climate, starting with the need for heat. And if you look at these Neolithic stone settlements on the top, they actually have a lot of similar features as the igloos on the lower two slides. So you'll see curved wall for providing protection from the wind. You'll see that the entrance is lower than the occupied space, so that cold air that enters through the door will stay low. And there's also a small hole at the top to release the smoke from the fire. Another historic example of heating, the Romans used a raised floor system called a hypocaust for heating their homes and also the Roman baths. So here you'll see that the floor sits on top of piers, and then a fire will create warm air, which is then drawn below the floor and up the stacks due to buoyancy or stack effect. We've talked about this before in terms of both infiltration and natural ventilation, where warm air rises. And a lot of Eastern cultures use the hibachi as a localized or decentralized form of heating. And since the homes didn't have a lot of insulation, it actually made a lot of sense to think about heating the people instead of the volume of space. So this 18th century hibachi on the left might burn charcoal, and that would be put under the table or sometimes under people's robes. And on the right, you can see a more contemporary electric version of this. Now, the European tradition relied on fireplaces. But one of the problems with fireplaces is you need one in every room, and you need to stay close to it to stay warm. So the upper image on the right, the Richmond Duke House, that was a 17th century mansion, one of Europe's greatest houses that's still in existence today. Below it, the Upton House, built around 1695. And with both, you see a number of chimneys sticking out of the roof. And that's a visible indication where every room had to have a fireplace because you could only be comfortable right in front of it. But we know the fireplace also had a lot of problems, right? The chimneys pull air from other spaces and openings in the house, and that'll make other parts of the house too cold. Another problem with open fireplaces, which is shown on the left in this 17th century Dutch painting, was that they generated a lot of smoke. And so the rooms would often be very tall, which would allow the heavy smoke from the fireplaces to rise. And because the fireplace is also pulling in air from other rooms and from open or leaky windows and doors, it would create a lot of drafts. And so on the right, you see a 19th century French painting that shows these four-poster beds with heavy drapes. And that was a way of keeping your body warmer at night in a very drafty house. On the left, what you're seeing here is a bit of an improvement. The house has an internal chimney, and that's a little bit more efficient because it's exposed on two sides, so the thermal mass of the chimney will warm up and will contribute to keeping the heat inside the house. So that was typical of the Northern European house plan. And on the right, this is a typical New England construction. It has brick masonry, and it's this particular picture is showing a timbered construction with a double chimney. So you can have one large flue, but fireplaces in two different rooms. So while those were improvements, overall, the fireplace really isn't that efficient, right? So you've got probably only about 10% of the heat energy contained in the wood is going to actually go into the house. So along came Ben Franklin, and he developed around in the 1940s the cast iron stove. And this is a considerable improvement over your basic fireplace. So it did a few things. The firebox was enclosed with small outdoor vents to supply the combustion air, and that limited the drafts that were created. The exhaust gases are also much hotter than in an open fireplace, so that you can create a stronger draft with a smaller diameter flue than the chimneys would require. And so you can have just a smaller stovepipe and create a pretty good draft. The cast iron stove was also pulled into the house, pulled inward, so it could be exposed on all four sides, and you could have greater radiant heat from all of the surfaces. So this became the standard method of heating throughout the 19th century in colonial America. So fast forwarding 100 years to the mid-1800s, Catherine Beecher was considered a reformer of the American household in the 19th century. And she was a pretty incredible woman, and she transformed a lot of fundamental ideas about our home to make it more functional. So in 1869, she designed what was called the American Woman's Home. If you're interested in this kind of stuff, there's a great book by Rayner Banham called Architecture of the Well-Tempered Environment. And there's a really nice section in there to learn more about Catherine Beecher. So she did a lot of great things in the houses. The one thing I want to point out here is she was really an innovator in creating a centralized heating system, which seems pretty conventional now, but it was fairly unusual for the 19th century. And so what she had was a furnace in the basement with a main central flue rising in the middle of the house with air ducts. And a really important feature of this was not just about heating, but there was increasing concern about foul air removal. So a lot of attention was paid to ventilation and the exhaust of the combustion gases. And the system also had a lot of these smaller ventilation flues identified as number 6 in this drawing, so that it would connect to the central flue and it would pull out air from the house and exhaust it and bring in fresh air, as shown in number 4. So moving on now, around the end of the 19th century, there was the cast iron radiator that was invented along with the steam heating system. So the sketch you see on the left is an example of an earlier system found in North America, where you'd put the boiler in the basement. That would make steam. The steam would rise under pressure through the building and then into the radiator. And then as heat was given off, the steam cools, turns into liquid, and water flows through gravity back down to the basement. And the radiators were typically placed under the windows, counteracting draft. But there's some problems with it. It tends to really to be very asymmetric, so it tends to intensely heat one side of the room but not the other. It can also be noisy. You can hear rattles and hammering. You could do it with water. So we have a lot of water perimeter radiators, and those require bigger pipes though, so that's one of the disadvantages. One of the advantages are that you can actually have more control though. You're utilizing sensible rather than latent heat. So it's not just on and off like the steam, you can also have volume control. And this system is in Worcester. Moving now to the early 1900s, the Roby House by Frank Lloyd Wright was part of a series of prairie-style homes built at the turn of the century. And it was one of the first examples of an open plan perimeter where there were really, there was really long bands of windows, which were lovely for view, and it worked great in summer. You could see the extensive shading. But the only way you could have these really large windows in cold Chicago was through the use of radiant systems. And every single window had a radiator below it, which I'm going to show you now in this picture. The left interior shot, you can see these trenches near the windows. And those are identified as number 6 in the right-hand images. And the lower right picture shows how these thin coil radiators are supposed to work. So what happens is you run hot water through a pipe, and that would conduct very easily to these thin metal films. So there's a lot of surface area. And then air trickles through the box and it rises up as it warms. And because the coldest part of the house is the window, that hot air rises and it warms the glass surfaces. So in general, this is really effective. The problem with this system in this particular building, that they didn't do it properly, there were no fins on the radiator. So it was just a pipe. It worked, but it really minimized the amount of heat transfer you get compared to if you had the fins. So 40 years later, Philip Johnson's glass house is in a very cold climate. He did things very differently. He wanted floor-to-ceiling glass on all the walls, incredible visibility, but this is a very uncomfortable environment to be in when it's very cold. The way he heated it is to have electric resistance heating in both the floor and the ceiling. He didn't want anything along the outside walls the way Frank Lloyd Wright did. And so you have these warm floors and warm ceilings, but then you have very cold walls. So in this case, there'd be a huge radiant asymmetry and probably a lot of drafts. So while radiant heat is great, electric resistance heating, the way he used, is really expensive. So the more common systems are to use hydronic water systems as your radiant systems. And this was tricky some years ago when pipes would corrode and break and cause people a lot of concern. But now they use this continuous plastic tubing called PEX. It's very flexible. It's really durable under temperature extremes. And it's installed as a continuous loop so that there's no place to leak. And there really hasn't been any problems with this system. All right, before I move on, I will ask if there's any questions. And Sierra, if you want to monitor the chat for me.
Sure, I don't see any questions so far.
Okay, thank you. If people have questions, go ahead and type them in, and then I will take breaks and come back to them. All right, so let's move on to the ventilation, the V in HVAC. So again, we're going to take a historical view. The first building to have centralized ventilation was the Houses of Parliament in London. And the smell of the Thames River was terrible. And so this building was really innovative in that it incorporated air ducts really high away from the river. So you can see that in the right side of this diagram with the inlets up at the roof. And what's interesting about this is how they actually move the air, because propeller fans were not invented until much later. So people had to use furnace stacks. They had to use heat as a way of moving the air. So you'll see in this upper left, it's the ventilating furnace and these gas burners shown in orange. I have a question. When I move my cursor on my screen, can you actually see it? Or do I just see that?
Yeah, we can see it.
Okay, good. Thank you. So here's what happens. It's pretty cool. So you have this ventilating furnace, and it's called a ventilating furnace because it's not for heating the space. It's for heating air. And you have these gas burners here. And the gas burners would then heat the air. Warm air rises. It would cause the air at the top of the building to rise. And as it's rising, it would pull in this fresh air, which would be from the inlet down through the basement and then would rise up. And then what was happening here down at the basement is that there were these really large wetted cotton wool ropes for filtering and evaporative cooling. And then the air entered the chamber down here, right under the benches of the Parliament members' terrace seating, so that that fresh cooled air was being developed or being delivered really close to the people. And this is an early example of what we call displacement ventilation, which I'll show you more later. We're still using that in contemporary ways where the fresh air is delivered low and then the exhaust is up at the top. Now, built 70 years later after the Houses of Parliament, the Larkin Building, which is no longer here, but it was in Buffalo, New York, again by Frank Lloyd Wright, was another first in how it was designed for ventilation. So this was the first hermetically sealed building because there was a lot of industry around there and a lot of pollution and smells. And so this was the first hermetically sealed and centrally ventilated building in the country. It was an inward building, very large atrium spaces that were surrounded by people working, what you're seeing in this diagram. Windows on the building are high. They're for light, not necessarily for air or views. And you see these large stacks here on the outside. And these large stacks that you're seeing in the left picture were architectural elements to express these large shafts that were needed to move the air. So you'll see in the center is the atrium. The air would then be drawn in at the top of the shafts, just like the Parliament building, down through these stair towers, and then back up into the occupied spaces. And similar to the Parliament building, it also had water in the basement for evaporative cooling and for filtering. And then the air would be circulated through these atrium spaces, and you'll see the air supplies under the balconies. Now today, the notion of providing fresh air in a building is typically just an afterthought. A building has to have fresh air intake. It's like the building is breathing. But oftentimes they want to hide those grills. So where do they put them? They put them in the back of the building, next to the loading docks, by the parking lot, because they want to hide them. But that means you might have all of these cars and trucks that are idling. So just because it's outdoor air doesn't necessarily mean that it's fresh air. All right, let's see. Are there any questions yet that people want to ask? No, don't see that. Okay, so moving on to history of a little historical perspective on the AC part of HVAC, which is air conditioning. So the air conditioning as we know it now was invented by Willis Carrier in 1902, and it was a really big deal. So some would argue that air conditioning was one of the greatest inventions of the 20th century, and it's enabled tremendous productivity gains and the ability to live in places that would otherwise have been really difficult. So we know that in the United States, since the 1950s, the fastest population growth in the US has been in the Sunbelt states. And this was largely driven by the availability of air conditioning. So here is the advertisements that I was showing you. So in the bottom left is the picture I showed you earlier, and here are a number of others. So in the 1950s, there was this huge movement to try to sell air conditioning to the homeowner. And a lot of these post-war advertisements were directly aimed at creating a new position for the modern woman. And the premise was that if you have air conditioning in your home, you could remain elegant and free from the toil of housework and face a day of leisure and luxury. So there was, as you can see from these ads, a very strong theme of fashion in the air conditioning advertisement that suggest an association between climate control and social status. There were also a lot of these advertisements that were aimed at women's pursuit of beauty, creating a more comfortable environment conducive to rest and relaxation. They were quite ridiculous in my mind, but they worked. Now, another thing that was interesting is that these air conditioning advertisements also attempted to shape our attitudes about nature. So there was this age of technology. People had an unshakable faith in the power of engineering. They had names such as Weathermaker. There were claims that you could have total mastery of the environment, creating the perfect indoor climate that was even more ideal than any place on Earth. So nature became this abstracted, almost sentimentalized ideal that could be manipulated. And a really interesting paradox here is that the advertisements would promote the environmental control technology's ability to match our desire for constancy and control, while they also used images and words that were associated with the more sensory and variable environmental qualities of nature. So far from the current standards that advocate neutrality as the ideal, these advertisements would speak of recreating springtime in the Rockies or the lazy warmth and comfort of June. Now, whereas the benefit of air conditioning is that it allowed growth in the Southwest parts of the United States where we couldn't build before. The use of air conditioning allowed us to build. The building really pushed the usage of air conditioning, but it also fundamentally changed building form and our relationship with streets and neighbors. So gone is the social dimension of the porch, what we often called the front porch society, where on a warm day, people would hang out and you greet your neighbors. Air conditioning has now seduced families into retreating into houses with closed doors and shut windows. And air conditioning has also had a profound effect on our sense of place, not only in residential neighborhoods, but also in cities. It's allowed us to build huge sealed buildings, big glass skyscrapers that look the same, whether they're in Houston, Texas on the left or Hong Kong on the right, and a host of other overheated places. And we couldn't do this without the ability to mechanically cool on a large scale. So before air conditioning, it would have been impossible to have these huge buildings with black glass. But I'm not sure this has actually done us any favors. All right, I'll take a break before I move to a new topic. Let's see, I see a question from Gabby. Any contemporary examples of buildings highlighting their ventilation systems, using them as an aesthetic element? Absolutely, and I'm going to be showing you an example later. A lot of times people are either using the shafts or the ducts, or just that's the distribution system we'll talk about, or there's examples where people are expressing the supply system, the interior, visibly. Worcester's not the only one to do that. All right, so I'm going to move to Next topic, which is near and dear to me, that I've done a lot of research on over the years, and I'm just going to have one slide here to give you an introduction to this concept of mixed mode. So one of the things I'm trying to do in this lecture is just be giving you an overview, the fundamentals, a language of HVAC so that it'll help you when STEP talks about advanced systems on Wednesday, and also in just talking to anybody else in the building industry, so you've got that common vocabulary. So the term mixed mode refers to the idea of combining operable windows for natural ventilation and some form of mechanical cooling. Now, the first thing people might say when you go, oh, I'm going to do mixed mode building is, I can't open the windows while the air conditioning is on. You know, you're supposed to close the windows for energy efficiency and keep all that coolness in the building. And that's true, but that's a really narrow view of what mixed mode is about. So the typologies of mixed mode are shown on the bottom here. On the bottom left, concurrent. That's what people usually first think of, is that the same space, same time, that the windows are open and the air conditioning is operating. And yes, while it's true that in the moment when they're both operating, that can be an energy loss, but just because it's designed to operate in the same space in the same time, it doesn't mean they're necessarily always operating at the same time. So you can control your set points so that the building is primarily in passive mode for most of the year, most of the day. And the mechanical cooling only kicks in to control the peaks. So yes, there may be some hours where they're both operating, but there's so many more hours of the year that you don't need the air conditioning at all because you've got the natural ventilation. Now, more commonly, you're going to have one of these other two kinds. The second one, the one in the middle, is changeover. That means they're in the same space, but you either have the air conditioning on or you have the natural ventilation on. So you're switching over. Either when the HVAC is on, there's window locks, or there's components of the HVAC system that are turned off when windows are opened by the occupants. So it can be one or the other. And it can be on a daily basis, it could be on a seasonal basis. And the third category on the far right is a zoned mixed mode system. And in this one, it may be operating at the same time, but it's in completely different spaces. So maybe you've got rooms that have a larger than typical cooling load, conference rooms, copier rooms, rooms on unshaded west facade because they didn't take 140 and know you need to shade, or maybe it's on the interior of a really large floor plate building. And so you group functions that have different needs, and some of them are air conditioning while others can be naturally ventilated. Any questions on mixed mode?
Any other questions so far?
Okay, thank you. So I'm going to move away from the historical and start talking about some of the basics of HVAC systems. I'm going to organize it by these general components of generation, or the source. How are you creating the heating or cooling? Distribution. This is the movement. How are you moving that heating and cooling around the building? And then supply, or how are you delivering it to the space itself? And any kind of system you're talking about, you can use this typology of these three main components or categories or phases of the system. And these typologies are going to be applicable to either conventional systems or high performance design. So on Wednesday, Stet's going to be elaborating on innovative systems. On the left is an example of a conventional system that you can either have everything in this rooftop packaged unit on top of the building, which is what is shown in this particular building, Or you can break it apart and have the centralized heating and cooling in a plant, in a centralized room. You can have the distribution and the supply all separated. So typically, as you're seeing on the right side, high performance buildings are generally not going to be these rooftop units. The functions are going to be separated. It gives you a lot more control about how you're designing different machines for each of these different functions. So this is an example of a rooftop system where everything's packaged in one place. You see a lot of these, and all of the elements are in one thing. They're delivered, they're popped onto the roof. Simple. If you're taking BART, you look around Oakland, you see these on top of all of the warehouses. So the advantage is that it's got a cheaper first cost. They're generally pretty awful from an energy point of view, however. All right, so let's start with generation. So with generation, we're going to talk about the generating the heating and cooling. In general, heating is much simpler than cooling. So I'm going to focus here on the cooling system. So in residential heating, you just might have a simple furnace. In a commercial building, you're often going to have these coils and air is going to blow over them. In these pictures of these hot water coils, those coils are going to look exactly the same if you're running hot or cold water over them. The difference is going to be how that heating or cooling is actually generated. So let's focus now on cooling since it's more complicated. So how do we cool? Well, this is what Willis Carrier invented, and it's the compression cycle. And there's some very familiar examples that everybody has a compression cycle in their home. It's the refrigerator, right? So the refrigerator is the most familiar example of a compression cycle. The basic idea here is that you have a cold side, in this case, inside your refrigerator, and the hot side where you're dumping the heat. And in this case, it's going to be the coils on the back of your refrigerator. You have a window box air conditioner, same thing. In this case, the cold side is inside your house. You're sucking air from that cold side to keep it cold, and you're dumping it somewhere. In this case, you're dumping it to the outside. So any of these systems, you're going to have a cold and a hot side. So how do you create those? I'm going to go over 3 basic principles that describe how the compression cycle works. So I'm going to go over the principles first, and then I'm going to go back to the compression cycle and explain how it works. So the first principle, when pressure goes up, temperature goes up. And a great example of this is when you're pumping up your bicycle and the valve gets really hot, right? You're increasing the pressure and the temperature is going to go up. Second principle at work, when the pressure goes up, the temperature at which phase change occurs goes up. What do we mean by phase change? That's when you're going from a solid to a liquid to a gas. In this case, we're always talking about liquid to gas, gas to liquid. That's the phase change we're talking about. Now, the most familiar example may be the same principle, but the opposite direction. When you're at higher altitudes, you're at a lower pressure, which means the temperature at which phase change or boiling happens is lower. And that's why it takes longer for things to cook, because things are boiling at a lower temperature. The third principle at work is something we've actually talked about before when we were talking about heat transfer. There's a phase, when there's a phase change, it's associated with an energy exchange. We talked about solid, liquid, gas are all higher energy states. So when you go from liquid to a gas, that's a higher energy state. It has to get that energy from somewhere, so it's going to absorb energy from the surroundings. When you go from gas to a liquid, that's going down to a lower energy state. So it's going to release its energy, or it's going to heat things. So when you go from liquid to gas, it's going to cool the environment as it's absorbing energy. when you go from gas to a liquid, it's going to heat up the environment as it's releasing its energy. So I'm going to now use these three principles and refer back to them when we describe the compression cycle. All right, so let's take a look at this. The compression cycle, an air conditioner, the basic thing that's happening is within that closed cycle, you've got a refrigerant that's moving around in the closed loop, and it's going to change pressure. There's going to be a high pressure and a low pressure side, and that's going to be associated with a high temperature and a low temperature side. So that's the main thing from this first diagram, and then I'm going to go to an expansion of it. But the main thing you want to know at this point is that you're moving a refrigerant around, and it's going through these two coils. Physically, they might look exactly the same, but because of this pressure difference, one's going to be a hot coil, one's going to be a cold coil, and the refrigerant is going to keep looping through it, changing pressure and changing temperature, changing from gas, changing to liquid. So let's see how that happens now. We're going to start with down here at the compressor. So what's going to happen here is that the gas is going to go through a compressor. Principle number one, what happens when it goes to a high pressure? It becomes a high temperature. So that was the first principle, right? So there's an electric motor, it drives a piston, it compresses the refrigerant gases. Think first principle, high pressure equals high temperature. So now you have the high pressure or the hot side. This gas then is very hot, and what it's going to do now is that hot gas is going to be sent through a coil. Now, when it's sent through a coil, it's hotter than its surroundings, so it's going to lose heat to its surroundings. As it's losing its heat, it's going to go through a phase change. Right? So a phase change here means the gas is then going to be cooled and become a liquid. And as it goes through that phase change from a gas to liquid, it will give up an enormous amount of energy that's released. And it's doing that at the high temperatures. So those are principles 2 and 3. High pressure, it's going to undergo phase change at that high temperature. So that's the hot side. And third principle, when it goes through the phase change from gas to liquid, it's going to release a lot of energy. So now you've got hot gas, which is now a warm liquid. The next step is that high pressure warm liquid is going to pass through an expansion valve. And what's going to happen there is that it's going to release its pressure through a tiny pinhole. What's the first principle? When pressure goes down, temperature goes down. So now you've got the low pressure cold side over here. All right? Let's take that cold liquid and let's just send it through another coil. It's cold. This is called the evaporator coil. The first one was condenser coil because you're going from gas condensing to liquid. Now this cold liquid is going to absorb the heat. It's going to cool the space that you're trying to cool. So as it absorbs its energy, what's it going to do? It's going to go through a phase change. So because it's a low pressure side, principle number 2, it can go through that phase change at the low temperature. Low pressure, low temperature. Principle number 1. Principle number 2, low pressure, phase change occurs at a low temperature. So now this liquid, as it starts to cool the surrounding space by absorbing its heat, it's going to evaporate. Principle number 3, when it goes through the phase change from liquid to gas, it's able to absorb an enormous amount of heat. Now you've got the warm gas, send it through the compressor again, and the refrigerant just keeps going round and round and round between high pressure, high temperature, low pressure, low temperature, going through its phase changes, releasing heat on the condenser side, absorbing heat on the evaporator side. This is the basics of the compression cycle. And when this was invented by Willis Carrier, it was pretty darn amazing. Now, Stet has talked about heat pumps. The heat pump is basically the compression cycle. A refrigerator is a heat pump. An air conditioner is a heat pump. But when we call it a heat pump, we're calling this, we're referring to that to the same kind of equipment, but if you flip it around, then the cycle is still the same, but depending on whether you're intending to cool a space on the evaporator side or heat a space on the condenser side, the heat pump can do both. It can either heat or cool. And you don't have to actually physically flip it around. You used to have to do that with the old systems. Now you just change the direction of the valve. So you're changing the direction that the refrigerant moves so that the side that's in your space is either the hot or the cold side. All right, any questions on this basic system? All right, so I've been using the example of a window box air conditioner or a refrigerator. I'm using these pictures of a little house. But when you get into a commercial building, right, and you're trying to condition a really large space, you have to move a lot of heat. So rather than air blowing over the coils, we know that water has a much higher heat capacity. And so what we're going to do there is we're going to replace the air side, just air blowing over these hot and cold coils. The refrigerant loop is going to be exactly the same. And now what we're going to do is on the condenser or the evaporator side, we're going to add an extra water loop. So let's do this first example on the condenser side. Which side is this? Is this hot or cold? This is the hot side. This is where you're removing heat from the building and you want to dump it to the outside. Well, with a window air conditioner box in your home, that's just sitting in your window and it's dumping it to the outdoors. Big buildings, you have to reject a lot more heat. So now what you do is you have a heat exchanger where instead of running air over the condenser, you're running water. And then you're getting hot water and you run that water up to what's called a cooling tower at the top of the roof. And you take that hot water and it's then sprinkled down these plates. The air blows past it, it cools, and then you have cold water that is returned. And it can be very, very large. So these are some examples of some cooling towers on top of Google Data Center. Now, similarly, on the evaporator side, the evaporator is the cold side. This is where you might be wanting to cool a building. Again, you're going to replace the air with water. And when you do that, a term that's often used is the chiller. So when you hear the word the chiller is just the evaporator side of the refrigerant cycle. But you're now chilling water rather than cooling air directly. So an air conditioner or refrigerator, you're running air over the coils. In this case, you're having a heat exchanger and you're chilling cold water. That's why it's called a chiller. And then you take that cold water and you circulate that through pipes to your building. And I'll show you a little bit more accurate system of how that's done. And these can be huge. This is an example of a chiller that actually has the cooling tower integrated into it, and it's going to then go on top of a roof. So this is going to be a package system that goes on top of the roof. All right, any questions on generation before I move to distribution?
There's a question on if the evaporation is happening at a lower temp than condensation.
Yes, good question. So that's where there's the cold side and the hot side, and that's equivalent to the low pressure and the hot pressure side. And the reason you have to change the pressures is so that as this refrigerant is doing loops, how do you get this one material, the refrigerant, to change phase in one direction and then the other direction? That's why the pressure difference is so important, because the pressure difference creates the hot and cold side, and it also creates conditions at which the phase change is going to happen in a different direction. It's pretty cool. Anything else?
I don't see any other questions right now.
Okay, thank you, Sierra.
Thanks.
So that's all the generation side. Now we've got to get that heating and cooling throughout the building. So how are we going to do that? We call that the distribution. Now we know that pipes are a lot more effective than ducts. They're smaller and they use energy, but there's a lot of systems that use air, and that's going to have tremendous ductwork. There was a question earlier about, are there other buildings that try to use architectural form for revealing distribution? And the Pompidou Center by Rogers and Piano in Paris is a really good example of that one, where it was explicitly going to be a very strong visible characteristic of the exterior and also the interior of the building. So you can intentionally try to expose and reveal the system, or you can intentionally try to hide everything. And the Seagram building by Mies van der Rohe in New York was one of the classic early examples of trying to hide everything. You could do it either way. It's an aesthetics decision that's up to the design team. So those ducts can be huge. How do we know how big they are? How do we control the room temperature? The basic principle of doing this is something you guys already know. You've already done this, and there's a good example that this equation would be on the final exam somewhere. It's basic stuff you've already know how to do. So if the amount of heat that's being delivered is proportional to the volumetric heat capacity of the material, in this case I'm saying air, but it can also be water. We're going to talk about air systems in a moment. The volume of air being delivered and the temperature of the supply air. Okay? So you can control how much heat is delivered to a space by either controlling how much air or what's the temperature of the air. Good example of this is you want to take a nice hot bath. How do you control the temperature of the water in the tub? You have your hot and cold water combinations. You can either bring in a lot of hot water, a little bit of hot water, right? You can control the temperature, you can control the volume, and ultimately get the temperature of the bath that you want. So how do we control how much heating is being delivered to a space? So you can control the volume, control the temperature. Most common in the past was controlling the volume. Controlling the temperature. The supply airflow rate is constant, so it's called a constant air volume system. And you're changing the supply air temperature to meet the thermal loads of the space. So most of these constant air volume systems are small. They serve a single thermal zone. And so let's just go through this diagram and start with the basics here. So what you're going to do is, somewhere not shown on this diagram is the basement. You have a boiler, you have a chiller, you're creating hot and cold water that is being delivered to these little blue and red coils right here. So your air comes into the building from the outside. It's going to run past these coils, let's say a hot coil on a cold day or a cold coil on a warm day, and it's going to move through the supply duct, and then it's going to come into the space, let's say through the ceiling. So once it's supplied, it's going to mix up with all of the room air, and then it's going to get returned. So the return air is the phrase we use of what's getting returned from the space. It's going to go through the return duct, and then some of it is going to be exhausted from the building, and some of it is going to be recirculated. And the reason it's not all recirculated is because you need some breathing air. And the reason in most buildings it's not all exhausted is that it would be it would be great to get 100% outside air, but it would be very energy inefficient because you have to then condition all of that outside air. So if the outside air is 50 degrees, 40 degrees, and you're bringing it in to heat it up, it takes an enormous amount of energy to heat that up. So if you're returning air at 70 degrees, why not recirculate that, right? So you're trying to strike this balance between indoor air quality and energy efficiency. Now, some spaces like labs are going to require you to do 100% outdoor air, but that's a different topic. So here you've got this system is that constant air volume, you're changing the temperature of the supply air by changing the temperature of the coils. It's responding to this thermostat. The problem with this system, as simply described here, is that it's only one zone, meaning one thermostat. So it's only delivering one temperature of the air. And if you're in multiple rooms, they may all have different kinds of needs. So that's what we refer to as thermal zones. Regardless how you're going to control the building, you're generally going to divide up the room into zones. And what does zones mean? Zones mean one zone, one thermostat. Just think of it like that. And different zones are going to have different needs, right? Maybe you're talking about the perimeter versus the interior. Maybe you're talking about different orientations in the space. Maybe you have rooms with different program, an office with one person versus a conference room. So how do we supply different levels of heating and cooling to these different zones? Well, if you start with the constant air volume system, even that simpler version, there's a way to modify that, if you will, so that you can provide zone control. And we do that with different systems. This one is called a terminal reheat. And it's what Worcester has, other than we don't have a mechanical cooling system, but we do it for heating. So the idea here, let's imagine a cooling system. So you're figuring out which room needs the most cooling. And you're cooling down here at the cooling coil. You're cooling down the temperature of the air to what the room with the biggest cooling need is going to have. And then you supply that air through the cooling supply duct to room 1, 2, 3. And then you take the heating coil and you have a reheat coil in each room. And in that way, since each room can have its own thermostat, one room may say, oh, well, that's perfect. And the second room says, no, that's too cold. You turn up the thermostat and the reheat coil turns on, and then that air is heated up a little bit before it's delivered. So each of those rooms can have different conditions. So the benefit here is that you've actually got really good control. What do you think a disadvantage is, though? How did I describe this? First,
Energy use.
yes, exactly. So you're cooling it down to what room needs the coldest air, and then you're heating it back up again. So that's pretty crazy, right? You're both cooling and you're heating. So the energy efficiency is terrible. So codes don't allow this anymore, except in maybe certain conditions where you need really careful control. And this is a picture of what a reheat coil is going to look like. And you can see these in Worcester. So when we get back to Worcester, which we're looking forward to at some point, in any of the classrooms, you look up at the ducts, and right where the duct comes into the room, you'll see the edges of these coils sticking out. And what you're seeing there is a terminal reheat coil. And that's where you can add more hot water to supply additional heat to a room to match its thermostat setting. Now, remember I said you can control how much heat's delivered by either controlling the volume or controlling the temperature. So everything I've shown you right so far has been keeping the volume constant and changing the temperature. Another system, which is much more common these days, is you're changing the volume, and it's called a variable air volume system, or VAV. So this is changing the amount of air rather than the temperature. So if some spaces need more cooling than others, instead of this old system with the little red boxes with a reheat coil, you have this green box here, which is a VAV, or variable air volume box. So it basically has a damper, and it looks like this. And what you're doing here is changing the amount of air that's delivered to the space. So you're not simultaneously cooling and then reheating. You're changing airflow, and this is a much more energy efficient system. It generally doesn't have as wide of a range of loads that it can cater to, though. And so you want to be really careful with any building to try to minimize your loads to begin with. And that's going to give you a menu of a lot more options. All right, so another system is, it's actually a complementary system to what we're talking about in terms of thermal control, and that's called a dedicated outdoor air system. And you'll hear people say DOAS. Engineers love to say DOAS, and you're going to go, what the hell are you talking about? Well, dedicated outdoor air system. So these are becoming much more popular. And the whole idea here is you're basically separating the ventilation and the thermal needs of the building. And as a result, this is going to give you a lot more flexibility in how you deliver and control the heating or cooling, and can do it a lot more efficiently. Because the amount of air you need for breathing is going to be different than the amount of air you might need for thermal control. So you want to separate those. So with a DOAS control, what you're seeing down here at the bottom is the DOAS system is controlling the amount of outdoor air coming in, just what you need for ventilation. So for that reason, there's no circulation. It's only about 100% outdoor air. And then you can have any system you want for thermal. So in this picture, it's designed with a conventional VAV system where all of the air can be recirculated, because any of the fresh air for breathing is handled by DOAS. Common example of these might be in hotels. It's a lot easier to distribute smaller pipes through the building instead of air. So there'll be a hydronic system for thermal, and then you could provide ventilation either through the outside window or an outside air vent, and you don't have to have big ducted systems running all through the space like the diagrams we've been showing so far. Another example is these are really common with radiant systems, where the radiant system combines the thermal conditioning and then the ventilation air is provided through the DOAS system. So we've shown you this early in the semester when we were talking in the first few lectures about volumetric heat capacity. Remember this? And we talked about how water has a much higher, over 3,000 times higher volumetric heat capacity of air. And back then we said, well, why is this going to make a difference? And we talked about how it means that the pipes can be much smaller than ducts if you're using water instead of air to distribute heating or cooling from the generation side to the room. You can move the same amounts of heat with significantly smaller amounts of water. So not only are the pipes going to be smaller than the ducts, but you also need much less energy to move the fluid. So the fans are going to take more energy than the pumps are, and also the fans themselves are typically much larger than the pumps. So you've got bigger ducts, bigger fans, you've got smaller pipes, smaller pumps. So that takes up much less room. Here, for example, is just a typical size of fans in a mechanical room compared to the pumps that you see in red in a mechanical room. So much, much smaller. All right, so the third component was of the system. We had generation, we had distribution, and then we had supply. How are you actually supplying the heating or cooling to the room. And this is the part that's most visible to people. We are the receivers of that thermal conditioning. So in an air system, you often have these air diffusers. It could be in the ceiling, it could be in the floor, they could be round, they can be square, they could have lots of different pictures. These swirl diffusers that you see in the bottom row, those are typically floor-based. And the diffusers that you see in the top row, typically ceiling-based. So just like how ducts can be intentionally exposed or hidden, so can the supply. Worcester's an example of everything intentionally exposed because the intention in that building was to teach architecture students about the stuff that goes into a building rather than hiding it. This is another example where everything's exposed. This is a zero net energy building we've shown you in previous lectures where they've intentionally exposed everything. On the ceiling, you see the air diffusers. It's very busy. You see the air diffusers here. There's also ceiling fans that are spinning here. They also, and those are considered part of the conditioning system. They have solar tubes. These are actually natural light coming in. And there's also fixtures here for electrical lighting. It has operable windows as part of the conditioning system. Lots of stuff going on, and it was intentional to expose that. But a lot of times there's a lot going on in a ceiling, and maybe the architects want a cleaner ceiling treatment. So the idea is to move a lot of this under the floor. So there's two different kinds of systems that I'm going to show you where you're providing the conditioning under the floor. The first one is called displacement ventilation. And this is the idea of intentionally stratifying the system where you deliver the air at the floor and you exhaust it at the ceiling. So it's often considered a better system for indoor air quality and also comfort. You're supplying both the conditioned air and the fresh air at the floor where the people are. And as the air warms up and rises, there's also a lot of pollutants that are generated in the space that are then going to rise up with that air. And the air at the top of the room is then going to be more polluted, and it will be extracted from a high return. So displacement systems are designed on the premise of separation or stratification. Whereas most of our air systems where you have a diffuser at the ceiling, it's designed with the principle of mixing. The intention is to mix up everything so that everything that is being generated in the room and other people's pollutants are all getting mixed up together. And I have a feeling that after this pandemic we're all going through, we might see an increase in these stratified systems as a way to improve air quality. So this is the system of displacement ventilation is actually more common in European systems. This example I'm showing you, and I'll show you the interior in a moment, is the Jewish Museum in Berlin by Daniel Libeskind. And this is a zigzag building design based on the two Hebrew letters spelling L'chaim, which means to life. He also designed the Contemporary Jewish Museum in San Francisco. If you've ever been there, that building's also based on Hebrew letters that spell out the word pardes, which means orchard. But I digress back to displacement ventilation. The interior is designed for the goal to be, for the system to be completely hidden. So can anybody guess where's the supply in this system? Does anybody see it? If you do, just unmute. Well, it's hard to see, and that was the intention, but if you look in this column, the hint is why am I showing this column? You can barely see this texture here. And that's the diffuser. It's embedded in the column, but it's painted. It's a perforated metal screen, and it's designed to be completely hidden. Now, here's another example of the Opera House in Copenhagen. Displacement ventilation is a very common system in these really large spaces. This is the interior, the main auditorium, where air is delivered below the seats. And this is a great example in large spaces like that, because you don't need to condition the whole volume of space. You don't really care about the air other than what you're breathing. So the cleanest air is provided very close to the people, and then you just let the warmer polluted air be gathered in the center and exhausted out the top. So this is another example. If you don't need to manage very high variable loads, the displacement ventilation works. If you do have higher loads, you might have to combine it with another system. This is an example in the Manitoba Hydro building in Canada, very cold climate, and it's got a lot of interior loads. So it was combined with a chilled beam system, and Stet's going to be covering that. So I'm not going to go into it in too much detail, and he might actually show you more about this building. What I do want to do, though, is talk a little bit about the next example of delivering air from the floor instead of the ceiling, and that's called underfloor air distribution, or the acronym UFAD. And this is something that at CBE, we spent a lot of years doing research on this. My colleague Fred Bauman wrote the design guide for underfloor air distribution, and we've been seeing a lot more increase in this. It's similar to a displacement ventilation in the way that it's being delivered low and extracted high, but UFAD generally encourages a little bit more mixing within the occupied zone while still allowing the stratification of the warmer polluted air up above. But it's a little bit more thought about lower, higher zones rather than a continuum. And there's been a lot of research that shows benefits of this system for energy savings, for comfort, for indoor air quality. It gives you a lot more flexibility to be able to move the ducts around. You might be able to control those diffusers. I meant to move the diffusers around. Sorry, you might be able to reach down and control those so that everybody can provide the amount of conditioning that they prefer and that they need. So this is just an example of showing some of that stratification, and this is an example showing how you might be able to reach down and move the diffuser yourself. So we've been seeing that build this system in everything from crazy Frank Gehry buildings to the New York Times building. And I've mentioned that UFAD is something that we've done a lot of research on. I see, before I go to the next slide, I see there might be a chat. Will you be covering geothermal heating and cooling? Let me ask, that's a great question, Roger. I know Stet is doing a lot of innovative systems, and let me ask him, if he's not otherwise covering it, if he can add something to that. Thank you for that. So when you took the tour of CBE and our building science labs, you saw that in addition to UFAD, we've done a lot of work on personalized comfort systems. So the UFAD was really one of the first systems we investigated where on a commercial scale, it was enabling people to reach down, control the diffuser, and provide the heating or cooling that they personally needed. Well, we wanted to take that a bit further and go, well, what if there was a retrofit option, not just dependent on the system, but a way to really move that personalized conditioning from the zone level down to the person level. So that you saw on the tour, we've done these foot warmers and the desk-based fans as shown on the left. We've done our heated and cooled chair as shown on the right. So I talked about that a little bit already. There are other people that are developing personalized ventilation systems. So this may actually be the future, especially given what we're all going through right now, of really trying to provide clean, fresh air right in front of the people. And there is an example of this building in Denmark, bank headquarters, where every single person had a personalized ventilation system. So it's not used very widely, but again, I'm kind of hoping that we might see more of that. So finally, I want to end by talking a little bit about radiant systems, and I'm pretty sure Stet is going to do more of this. It's one of his favorite systems, and he's going to be great at showing us more case studies. So I'm just going to go through some of the basics of how this works. Air systems is what we've mainly been talking about. The idea is you're delivering conditioned air to the space. You could be doing it from the ceiling, you could be doing it from the floor. And what you're trying to do in terms of comfort conditioning, by conditioning the temperature of the air, then you're just affecting our convective exchange from our body. The good thing about air systems is you can address temperature, you can address humidity issues, you can address ventilation. So in some ways it's good because it addresses all of those things. In some ways it's really hard if you're trying to make one system do all of those things. The purpose of these is to actually intentionally try to just use air as your metric for saying what is it that makes us comfortable. But we also know from our comfort lecture that we exchange energy with the environment in a variety of ways. We're exchanging energy by convection to the air, but also by radiation to the surrounding surfaces. So what a radiant system tries to do is control the temperature of those surfaces so that it's controlling our comfort through both convection and radiation. Now, it doesn't do anything for humidity control. It doesn't do anything for ventilation. So that's where it's really common for radiant systems to be combined with these DOAS systems that I mentioned. It's a lot more complex. So too often I think designers just do cookie cutter approach to radiant systems. But after CBE did years of research on UFAD, we've been doing a lot of research on recent years on radiant systems and generated a great deal of publications and developing design tools right now. So one of the things we're hoping to do is make it easier for designers to use these systems, because we think they have enormous opportunities in zero net energy buildings and to reduce energy use while also providing comfort. So one of the things we developed through a former PhD student is this building project map, and we're doing this for other systems as well, which is enabling people to figure out where else has this been done. And we find that engineers are really reluctant to try something new for the first time. So that if we can start documenting where projects have utilized these systems, then you can use this map. You can add your own project. You can find out where there's other case studies and see if it's something that can be used in an example that's relevant to your own project. So there's different ways to use radiant systems. One is called thermally activated building systems, or TABs. And the far right, the radiant panels. And then in the middle, there's kind of a hybrid of the two. The main difference here is whether or not you're using some kind of thermal mass along with the radiant system. So I think a better way to show this is going to be on this one, which is going to be my last slide, and then I will let Stet continue with this with some of the case studies that he's used from his professional work. So the TABs versus radiant panels. This is the heavy mass versus no mass. So the heavy mass systems, the thermally activated systems, Those are integrated into the slabs, either from the ceiling or from the floor. Both of these systems provide heating and cooling. The biggest difference, though, is that when you embed it in mass, we know how mass works, right? It's good and bad. It's good in that you can flatten out the peak loads, which is really important, but it's bad in that there's a much slower response. One of the benefits of the radiant panels is that it's a really quick response, so it's easier to control. So you might use these in different spaces. For example, I've seen the lightweight radiant panels be used in rooms like conference rooms. So you have intermittent occupancy. We talked about that back in the thermal mass lecture. If you have a room where there's going to be people who come in quickly and all of a sudden the cooling load goes up, you need response quickly, the radiant panels are a good way to do that. The system on the left, the tabs for the thermal mass slower response, that may be better for general office space, for example. You're trying to flatten the peak loads, you're trying to create more even and uniform distribution. Another advantage which enables you to reduce the peak loads, Stet and I have both talked about this, where when you look at the cost of energy and the impact on the grid, wouldn't it be great if you could actually generate that cooling in the evening when the rates are cheaper, when you're not impacting the grid, and then you pre-cool the space by pre-cooling that mass, and it lets you float over a longer period of time. So there's pros and cons in different kinds of spaces. And then the last bullet on each is the relative cost, that the tabs is a much less expensive system. So particularly if you're going to be doing it for large surface areas, that's really the way to go. So with that, I'm going to end there, but I will hang out. I will take questions about the lecture. I'll take any questions about the class in general. And then just a reminder that we've got our last quiz on Wednesday. We've got on Wednesday, Stet's lecture is really a good one because I value the experience he's bringing in so much. And so he's got a lot of great case studies and stories that he's going to be telling. And then on Monday, we used to have a tour of the Worcester Mechanical System, which I love doing. And unfortunately, we can't do that this year. So instead, I'm going to give you a lecture I'm pretty excited about. I've done it as a keynote lecture in several places, internationally even, and it's about the value of variability. And it's going to go from systems back to people, and going to talk about experiential qualities of space and how we can get away from this idea of neutrality and constancy and how that can enrich our well-being. So it's a topic I really love a lot, and looking forward to sharing that with you on Monday. So with that, I'll close down the lecture. Thank you, but I will hang out if anybody's got questions.
Thank you.
You're welcome.